How are the elements of the periodic table made? A very deep question is, how are atoms made? As soon as you ask that question, you're also asking the question, how are we as people, or the planets and stars, how are they made? It's a very, very, very deep question. In order to answer this question, we will describe three processes that create the entire periodic table. However, it's more complicated than this. So these three processes give you the general idea. In order to really understand that, it is beyond the scope of this course to be able to describe how all of the atoms are made. These three processes are the Big Bang model, stars, and supernova explosions. The Big Bang. Collisions between high-energy particles tell us how the universe was moments after being created. Cosmological models that describe the expansion of the universe, not the creation, is called the inflationary Big Bang model. In a nutshell, the model predicts the universe starts from nothing to something. Then in an instant, there was not just something, but everything that would ever be, and all at once. Starting with a very high density and temperature region, the universe swiftly expanded and cooled along the way. From Einstein's energy relationship, which says that E squared is equal to this quantity squared plus mc squared squared, this says that the total energy on the left side is equal to a kinetic energy term plus a mu mass potential energy term. What this equation tells us that in the inflationary Big Bang, what it did here is it created an enormous amount of energy. And now that I have all this energy, which is a form of potential and kinetic energy, part of that is created into mass. And it is this mass that is the birth of particles. Once again, this mass, which comes from the energy of the Big Bang, you have some of it converted into mass, which then gives you the birth of particles, like the elements in the periodic table. Nature seeks the state of lowest energy, which translates, in this case, to the state of lowest mass particles. A very key picture to understanding where we're going here is something that's called the history of the universe. So what you're seeing right here, this is the so-called Big Bang. So the universe, after it has its initial Big Bang, there's a period of what is called the inflationary period. And what happens here during the inflationary period is that the universe expands extremely rapid. And then there's a period where this inflationary thing ends. During the next phase of the expansion of the universe, the only matter particles that exist here are things called quarks and electrons. And it is quarks that, as the universe expands and cools, that they then form protons right in here, and neutrons. That is, as the universe expands and cools down enough, protons and neutrons are formed from these things called quarks. Here's the important piece. With the ongoing expansion of the universe, after 380,000 years after the initial Big Bang, the universe has cooled to a few thousand degrees. That's less than the temperature of the sun, so that the electrons could latch onto nuclei and form their first 4 atoms on the periodic table. So that means that it produced hydrogen, roughly 75%, helium 25%, and lithium and beryllium were just trace amounts. So if you were to look at the history of the universe, this occurs right here. And there is so much strong evidence for this that, in fact, 2 Nobel Prizes have been given for this type of information. So let me say this again. At 380,000 years, you had a combination of primarily hydrogen and helium. So during the dark ages, if you were to look up into the sky, you would see no stars. That's why it's called the dark ages. And what you find here is that the first stars are not made till after 200 million years. So for 200 million years, the skies are completely dark. And this brings us to the next stage. The second stage is stars. And then it is stars that start to produce more atoms. 2. Stellar nuclear synthesis. That is, stars are the engines for creating new atoms. So now I have a universe filled with hydrogen and helium. Gravity is the great engine of cosmic clumping and pulls them inwards. It pulls in hydrogen and helium to form giant gas balls with epic pressures inside their cores. These are the first stars ever made. At such pressures and temperatures, nuclear fusion occurs at the cores of stars. Under these extreme conditions, two protons collide and go inverse beta decay. Picture-wise, you could see a proton and a proton. When they collide, one of these protons turns into a neutron, and this inverse beta decay creating deuterium. Then nuclear fusion begins. By fusing two hydrogen, deuterium, and a proton, you then create for the first time helium-3. In other words, these hydrogen atoms don't exist anymore. Only this helium nuclei exist. That is, the consumption of hydrogen creates heavier atoms. In this case, it's helium. But this consumption of hydrogen produces gamma rays. And in gamma rays, this is the light that's emitted by a star that we typically see. And the fusion of hydrogen nuclei uses up hydrogen. In other words, it consumes hydrogen. And as you consume hydrogen, you produce helium nuclei. And in this process, you release energy. Hydrogen is the fuel for this process. As the hydrogen fuel is used up, the core of the star condenses and heats up even more. Then helium becomes the fuel to fuse the next atoms in the process, like lithium and beryllium. But you need higher heats in order to fuse helium, which is a bigger atom than hydrogen. And the process continues. And then you go to boron. And then you go to carbon, nitrogen, oxygen. It turns out that the sun can only fuse up to oxygen. Our sun can only fuse up to oxygen because it's a smallish sun. That means it doesn't have enough pressure and temperature in order to fuse anything higher than oxygen. To create elements higher than oxygen, like fluorine and neon, the core of the star gets hotter and hotter and hotter. And it gets denser and denser and denser, which starts to lead to the star becoming more and more unstable. You keep going through this list of atoms, and the very last atom that can be made in stars is iron. So iron is as far as nuclear fusion processes can go. When hydrogen fuses to produce helium, abundant radiant energy is produced to stop gravity from collapsing the star. So I have the radiant pressure from the inside pushing outwards, and that's being counteracted by the force of gravity pushing inwards. To fuse heavier nuclei, the star must get hotter and hotter, but there's a cost. The star grows more and more unstable. In order for a star to survive, the radiant pressure has to match the force of gravity. We can understand why a star becomes unstable as it starts to burn heavier nuclei by looking at the binding energy curve. And what we want to look at is we want to look at differences in energy released during nuclear fusion. So nuclear fusion only occurs to the left of the blue line. the biggest energy release occurs by fusing hydrogen, which is at 0, all the way up to helium-4. So if I fuse 4 hydrogens to produce helium-4, I could think of this as a bar diagram. This is how much energy 4 individual hydrogens have. This is how much when I combine them to form helium-4. This extra energy, gamma, which is from 0 all the way up to where helium-4 is the energy released in this process when you fuse them. There is a smaller energy release when fusing carbon-12 and hydrogen to form oxygen-16. Let's look at this on the graph. In a bar diagram, if I have carbon-12 and hydrogen, and it has this amount of energy, then most of that energy is actually going towards the oxygen and very little energy difference between these two. So the energy emitted is getting smaller. When nuclear fusion gets to iron, there's a big problem. You could see that iron is at the peak of the curve. Because iron is at the peak of the curve, no energy can be extracted via nuclear fusion. Analogy: when a blazing fire burns up wood, it transforms every bit of its fuel, in other words the wood, into ash where all of its energy has been used up. This implies that no energy can be extracted from ash. That is, one cannot burn ash to generate heat. Iron is the ultimate nuclear ash. No energy can be extracted by fusing iron with anything. So, when a massive star produced its inevitable iron core, the game was over. The results are catastrophic. There is no more radiant pressure. Before a star reaches an iron core, the radiant energy was balanced out by the force of gravity. So I had an equilibrium situation. When a star forms an iron core, the radiant energy is no more. It's gone. The only thing that's left is this force of gravity and this iron core. So what happens? The force of gravity instantly collapses this star. In summary, nuclear fusion produces nuclei up to atomic number 26, which is iron. Nuclear fusion cannot produce anything above iron and requires an extreme situation, which is now a supernova. We just discussed how trying to use iron is not possible to generate radiant energy to stop gravity from collapsing a star. When a star collapses inward on itself, this is due to the force of gravity pushing it down. It rebounds off its dense core and explodes as a supernova. This sudden compression generates such intense energy that the brightness of a supernova outshines an entire galaxy. During a supernova process, there are two new nuclear processes we have not discussed. There's a rapid nuclear and a slow nuclear process. The rapid nuclear process, also known as the R process, that occurs during the compression and the sudden explosion, whereas the slow nuclear process, known as the S process, that's after the sudden explosion. In the R process, it produces about half of the elements heavier than iron, whereas the S process produces the other half of the heavier element. When big stars exploded as supernovas, they seeded space with the elements they had created. Elements like carbon, oxygen, nitrogen, phosphorus, and sulfur, the elements of life, were especially abundant, as well as all of the metals. Magnesium, silicon, iron, aluminum, and calcium, which dominate the compositions of many of the common rocks, formed a large fraction of the mass of Earth-like planets, also abound. But rarer elements like silver, gold, copper, as well as radioactive uranium and plutonium were also made in lesser quantities. All these elements were hurled out into space where they could find one another and clump together. Question: my wedding ring is made out of gold, which was clearly mined here on Earth. However, the Earth and Sun is not capable of making gold because it doesn't have enough high temperatures and pressures to do so. Where does the gold come from? It's stardust. It's the dust produced by supernovas. So these supernovas, they produce cosmic seeds. And when our solar system was formed, these atoms from these long dead supernovas that make you, me, and my gold wedding band today are the result of stardust.